11 billion miles from Earth, in November of 2018, something happened to a 41-year-old spacecraft that scientists had been waiting their entire careers to witness. Its instruments recorded a sudden, dramatic drop in the particles streaming outward from our sun. In their place, colder, denser material began flooding in from somewhere else entirely. For the second time in human history, and the first time with an instrument actually capable of proving it beyond doubt, a machine built by human hands had left the protective bubble that surrounds our entire solar system and sailed directly into the space between the stars. This is the story of Voyager 2, the quieter, less famous twin, and how its crossing into interstellar space actually taught scientists more than its sister ship ever could, revealing a boundary stranger, thinner, and more precisely structured than anyone expected to find out there. To understand why this moment mattered so much, and why scientists were, in the most literal sense of the word, shocked by what they measured, you have to go back 6 years earlier to Voyager 1's own crossing, because that first crossing left behind a mystery nobody could fully solve. In August of 2012, Voyager 1 became the first human-made object in history to leave the heliosphere, the vast, invisible bubble of solar, wind, and magnetic field generated by our sun that surrounds all 8 planets and everything we have ever directly explored. Crossing that boundary, called the heliopause, meant leaving the environment shaped by our own star behind entirely and entering the interstellar medium, the thin, cold material that fills the space between star systems, seeded over billions of years by the remnants of ancient supernovae. It was, without exaggeration, one of the most significant milestones in the history of space exploration. But there was a problem. Voyager 1's plasma science instrument, the single most direct tool for measuring the actual density, temperature, and speed of the solar wind and the material replacing it, had stopped working back in 1980, more than 3 decades before the crossing even happened. Scientists had to infer the crossing indirectly, watching cosmic ray levels climb and heliospheric particle counts fall, piecing together a picture from secondary evidence rather than a single, clean, direct measurement. It took almost a year after the fact, using a completely different instrument that happened to catch a burst of plasma oscillations, before the team could confidently confirm that Voyager 1 had actually left. Even then, the transition itself turned out to be messy and confusing, unfolding over nearly a month, with the spacecraft appearing to drift in and out of connection with the solar wind before the boundary was fully crossed. That left an open question hanging over the entire achievement. Was interstellar space really that close and that irregular? Or was Voyager 1's crossing simply harder to interpret because its best instrument for the job had died decades earlier? Voyager 2 was going to answer that question because, unlike its twin, Voyager 2's plasma science experiment was still alive. Voyager 2 had followed a very different path than Voyager 1. While both spacecraft launched in 1977, just 16 days apart, Voyager 1 took a faster, more direct route past Jupiter and Saturn before angling up out of the plane of the solar system entirely. Voyager 2 took its time, using its own careful sequence of gravitational slingshots to become the only spacecraft in history to fly close by all 4 of the solar system's giant planets: Jupiter, Saturn, Uranus, and Neptune. A genuine grand tour that no other mission before or since has managed to replicate. That longer, more deliberate path meant Voyager 2 crossed the heliopause on a completely different trajectory, heading out of the solar system's southern hemisphere rather than the northern one Voyager 1 had taken. And crucially, it still had a functioning window into the plasma directly around it. On November 5th, 2018, at a distance of about 119 astronomical units from the Sun, roughly 11 billion miles, Voyager 2's plasma instrument recorded exactly what scientists had been hoping to see for over 4 decades. A sudden, steep drop in the speed of the solar wind particles surrounding the spacecraft. And then, nothing. No further solar wind flow at all. At the same time, 3 other independent instruments aboard the spacecraft, the cosmic ray subsystem, the low-energy charged particle detector, and the magnetometer, all recorded readings consistent with the same conclusion. The solar wind that had surrounded Voyager 2 for its entire 41-year journey had simply vanished, replaced by the colder, denser plasma of true interstellar space. This time, there was no ambiguity, no year-long wait for indirect confirmation. The data was immediate, direct, and unmistakable. Ed Stone, the Voyager project scientist based at Caltech who had been with the mission since before launch, described the moment with the kind of careful understatement that scientists tend to reach for when something genuinely extraordinary happens. There was still, he noted, a great deal to learn about the region immediately beyond the heliopause, even with this new, cleaner data in hand. Suzanne Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, put the feeling of the moment more plainly, admitting that the team felt both happy and relieved that both spacecraft had managed to survive long enough to reach this milestone at all, and that the entire mission had, in many ways, been building toward the chance to finally study interstellar space with 2 independent vantage points at once. And this is where the real shock came in, because when scientists compared Voyager 2's clean direct crossing to Voyager 1's messier indirect one, they found something nobody had fully anticipated. Despite crossing the heliopause on completely different trajectories in completely different hemispheres of the heliosphere, separated by 165 astronomical units of distance from each other, and during dramatically different phases of the Sun's roughly 11-year activity cycle, both spacecraft crossed into interstellar space at almost exactly the same distance from the Sun. Voyager 1 crossed at about 122, 6 astronomical units. Voyager 2 crossed at about 119, 7. A difference of less than 3 astronomical units across 2 crossings separated by 6 years and an entirely different direction of travel. Stimasios Krimigis of Johns Hopkins University, one of the scientists who analyzed the results, called the similarity remarkable, and it genuinely was. It suggested something almost nobody had confidently predicted before these 2 data points existed: that the heliosphere, the bubble our Sun carves out of interstellar space, is far more symmetric, far more uniform in shape, than the messy, unpredictable picture painted by Voyager 1's crossing alone had suggested. Bill Kurth, a research scientist at the University of Iowa who worked on the plasma wave instruments aboard both spacecraft, described it in almost architectural terms. The heliosphere, based on this comparison, behaves less like some irregular lopsided cloud and more like a blunt, rounded structure pushing steadily against the interstellar medium from 2 nearly matching distances on opposite sides. Don Gurnett, another University of Iowa's scientist central to both missions' plasma wave analysis, went further, arguing that the old assumption that the solar wind simply fades out gradually the farther you travel from the Sun was flatly wrong. What both spacecraft actually found was a distinct, comparatively sharp boundary, not a slow tapering off, but something closer to an edge, a genuine transition point where one environment ends and another begins. But the comparison also revealed real, meaningful differences. And those differences turned out to be just as scientifically valuable as the similarities. Voyager 1's crossing had taken nearly a month to fully unfold, with the spacecraft appearing to dip in and out of contact with the solar wind multiple times before the transition was complete. Voyager 2's crossing, by contrast, was almost startlingly quick, completing in less than a day. Ed Stone, reflecting on the difference, noted that Voyager 1 had actually detected brief connections back to the heliosphere even after it seemed to have left, while Voyager 2 showed the opposite pattern, appearing to remain connected to lingering particles leaking outward from inside, even after its own instruments confirmed it had crossed over. Scientists have proposed that this difference may be tied to where each spacecraft happened to be relative to the Sun's activity cycle at the moment of crossing, with Voyager 2 passing through during a period when the heliopause itself may have been actively contracting inward, effectively moving to meet the spacecraft partway. Magnetic field data added another layer of intrigue. In both crossings, scientists expected the direction of the magnetic field to shift noticeably once each spacecraft left the heliosphere and entered the differently magnetized interstellar medium. In both cases, that expected shift largely failed to appear, a genuine puzzle that researchers are still working through, and one that suggests our understanding of how the Sun's magnetic field interacts with the wider galactic magnetic field beyond it remains incomplete in ways the original heliopause models never anticipated. There was also the matter of temperature and density, and here Voyager 2 delivered something Voyager 1 never could, because its plasma instrument was actually functioning. Scientists were able to directly measure the plasma surrounding Voyager 2 immediately after the crossing, and found it sitting somewhere between 30 and 50,000 Kelvin, remarkably hot for material that is technically part of the cold interstellar medium, likely because the plasma gets compressed and heated as it collides against the outward pressure of the heliosphere itself, the same way air heats up when compressed rapidly. At the same time, that plasma proved to be significantly denser than the plasma inside the heliosphere, confirming something Voyager 1 had only hinted at from a distance, that the boundary of our solar system doesn't just mark a change in composition, it marks a genuine compression zone, a place where 2 very different environments are actively pressing against each other, piling material up along the edge where they meet. None of this was quiet. Background science conducted in isolation. 5 separate teams of researchers, working independently, published their analyses of Voyager 2's crossing together in the journal Nature Astronomy, comparing notes, cross-checking conclusions, and building piece by piece the most detailed picture humanity has ever assembled of what actually happens at the edge of our solar system. And what emerged from that combined analysis wasn't a tidy, simple answer. It was a more complicated, more textured understanding of the heliosphere than the clean diagrams and textbooks had ever suggested, one where the boundary is real and comparatively sharp, but also asymmetric in subtle ways, compressed and shaped by forces still not fully mapped, and stranger in its magnetic behavior than either crossing alone could explain. It's worth pausing on just how much lower the stakes for error were with Voyager 2 compared to Voyager 1, and how much that mattered. When Voyager 1 crossed in 2012, scientists were essentially trying to prove something extraordinary had happened using indirect evidence, secondhand signals standing in for a direct measurement that no longer existed. 6 years later, Voyager 2 handed them exactly what had been missing. A direct, unambiguous, instrument-confirmed measurement of the transition itself, captured in real time as it happened, complete with density, temperature, and particle flow data that left essentially no room for alternative interpretation. That difference between inferring a boundary crossing after the fact and actually measuring it as it occurs is the difference between a hypothesis and a confirmed fact. Voyager 2 didn't just repeat Voyager 1's achievement, it validated it, and invalidating it opened up an entirely new, richer set of questions about the true shape and structure of the bubble that protects our entire solar system from the radiation of the wider galaxy. Since that crossing, both Voyager spacecraft have continued sending back data from interstellar space, and the picture keeps deepening. Together, they've helped confirm that the heliosphere shields Earth and the rest of the solar system from more than 70% of the cosmic radiation that would otherwise be striking us directly, radiation generated by exploding stars scattered across the galaxy. They've shown that the plasma of interstellar space is measurably colder and denser than anything inside the heliosphere, exactly as theory predicted, but with subtle compression effects on both sides of the boundary that nobody had fully modeled in advance. And scientists have confirmed that even now, years after their respective crossings, both spacecraft appear to be sitting in a turbulent, disturbed transitional layer just beyond the heliopause, rather than in the calm, undisturbed depths of true, unaffected interstellar space, meaning even this boundary itself carries more internal structure and complexity than the phrase edge of the solar system tends to suggest. As of now, both Voyager 1 and Voyager 2 remain the only two spacecraft in human history to have operated beyond the heliosphere, and they remain, even decades after launch, the only direct source of information we have about what that transition actually looks like from the inside. There is no other mission currently active anywhere near that boundary, and no successor mission funded or built to replace them. Every reading, every data point, every subtle confirmation or contradiction of the models, built from decades of remote observation, comes from these same two aging spacecraft. Still communicating, still working, long after anyone reasonably expected them to. What makes Voyager 2's crossing so quietly remarkable, even years after it happened, is how much confidence it added to a discovery that had, until then, rested on partial evidence and careful inference. It turned Voyager 1's historic but ambiguous departure into something scientists could actually stand behind with full certainty, while simultaneously revealing that the boundary itself is neither as simple nor as uniform as the first crossing alone had implied. It gave researchers two independent points of reference, on opposite sides of the sun's protective bubble, confirming that our solar system's edge is real, physical, and measurably distinct, while also proving that edge is shaped by forces, magnetic, thermal, and dynamic, that we are still working to fully understand, even now. We spent most of human history assuming the solar system simply faded into nothing at its outer edges, a boundary too faint and too distant to ever really define. Two aging spacecraft, launched weeks apart in 1977, built with less computing power than a modern calculator, proved that assumption wrong not once, but twice, from two completely different directions, 6 years apart. And in doing so, they didn't just mark the edge of our solar system. They handed us the first real evidence of what it actually looks like to leave home for good.